All right, so last time we met, we talked about exponential equations. We had a little bit of an overview. We spent most of our time talking about exponential equations. And today we're going to finish up one special type of exponential equation. And then we're really going to spend the bulk of our time taking a look at log equations. All right, the big theme, more important than anything else as we're going through this, is for us to think about our decision making. We're going to learn so many strategies, but it's so important that we know what strategy to use when. And that's something that I want us individually to be able to internalize, okay? So we took a look at a few different types of equations. We talked through our process. And that would be something that if you're not clear on the decision making, maybe go back and rewatch those videos, or pop by office hours or pop by Ethan's tutoring sessions. But making sure you know when to use what is going to be super, super important. All right. Now we went through some really long equations, and we're going to finish up one last type of exponential equation right here. Okay. I think it is next week, but next week in 15C, you'll be looking at factoring, okay? And so factoring is sort of notoriously one of those topics that students either really get, or they think, I hope this goes away so that I never have to actually learn it, and then it'll just go away and I can move on with my math career. I have some really bad news for you if you're in that camp. And the bad news is that I have taken a lot of math classes, and I've never taken a math class where I didn't need to factor. And I want to be really clear about that. When I say factor, I mean factor. I do not mean quadratic formula. You're sitting here being like, I don't know how to factor, but I know how to use that quadratic formula. That is a place where I would like us to move forward, in the sense that by the time we hit December, like the end of our semester, that we feel really confident in factoring without the quadratic formula. Okay, so I think the next 2 weeks in 15C are meant to be very heavy on the factoring. Okay, it's a skill that, if you don't know it, can really hold you back. But once you know it, once you feel confident in it, no matter how much work it takes to get there, but once you get there, it keeps so many doors open in terms of math. Okay. And so I don't want that to be something that potentially holds us back. I want that to be something that we see very much as a strength. Okay. And so with that, we're going to take a look at example 8 and example 9. Okay. All right, so we're going to take a look at example 8 here. And what we're going to do is we're going to go ahead and multiply both sides of the equation by something, okay? And I'll sort of say for right now, like kind of go with it for right now, but as these questions come up about why we're doing it, I hope we'll answer that as we go through the question, okay? So my first step here is I'm going to take the equation, and on both sides, I'm going to multiply by 3 to the power of x. Okay. So all I'm doing right now is multiplying both sides by 3 to the power of x. And this is something I can do with all equations in general, that whatever I do to one side is fine as long as I do that same operation to the other side. Okay. But here's what's going to happen. Once we multiply both sides, we're going to distribute that 3 to the x to the first term, and we're going to distribute it to the second term. And then over here on the right-hand side, we're going to distribute that 3 to the x to the 28. And before we sort of continue in our simplification, I want us to be really rooted in this idea of order of operation. Okay. We need to make sure that we hold up our order of operations as we move forward. Okay. It's one of those things that, like, yeah, when someone says follow the order of operations, we're all fine and good. But if someone doesn't explicitly tell us that, then sometimes we just don't follow them. Okay. And that's where a lot of sort of illegal stuff starts to happen. So when I multiply, here's what I get. I get 3 times 3 to the x times 3 to the x plus 9 times 3 to the x times 3 to the negative x equals 28 times 3 to the x. Okay. So all I've done is distribute that term in there. Now, if we take a look at what we have here in this first term, I have 3 to the x times 3 to the x. What is another way that I could write 3 to the x times 2 to the x?
3x squared.
Nice, nice, nice. Okay, so in this next line, I'm going to write 3, right? Because I still have this 3 out in the front, so that's this one. But instead of writing 3x times 3x, I'm going to write it as 3x squared. In other words, this in the yellow came from the things in the yellow in the previous line. Okay. Plus 9. And what's another way that I can write 3 to the x times 3 to the negative x? This might be helpful to think about some rules of exponents that we may have learned at some point in our academic career.
1.
How'd you get 1?
Since you're multiplying powers, they cancel each other out, or you either add and subtract rather than multiplying them. So x minus x is 0.
Good. So I'm gonna thank you for explaining that so thoroughly. I'm gonna write that out for us, right? So what was said here is that if we have the same base, right, 3 on both of them, and I'm multiplying, then this power and this power, I end up adding them, right? So I get x plus negative x, or x minus x. And if these exponent rules are a little sort of deep in your brain, not as accessible as you want, the Desmos activity for today, that is due today, does go over rules of exponents again. Okay, so it's meant to support us in these little pieces that we're like, oh, we learned them once upon a time, but you know, it's just not as fresh as maybe we want it to be. Okay. Now, if we keep simplifying just a little bit more, I'm going to do 2 things in this next step. Okay, I am going to say that 3 to the 0 power will give us 1. Okay, 3 to the 0 power will give us 1. A number to the 0 power will give us 1. And that is a common thing that comes up for us. Okay, and so you're going to see a lot of examples where I try and make those happen in the equations so that we get a chance to practice that. The other thing I want to do is I want to take this term on the right-hand side and I'm going to move it over to the left-hand side. And so I end up with 3 times 3 to the x squared minus 28 times 3 to the x. That's the term from the right-hand side that I moved to the left-hand side, plus 9. 9 times 1 is 9, equals 0. Okay. Now, why did I start class today by talking about factoring? Because sometimes when we have equations that are rather complicated looking, if we, I'm going to call it distill, if we distill it down to a more familiar form, it allows us to solve that equation and then take care of the part that is new for us later on. And here's what I mean by that. We are going to let u equal 3 to the x. And all I mean by that is everywhere in my equation where I see 3 to the x, I'm going to replace that with the letter u. Okay. By the time we get to the spring in Math 150, you'll understand why I'm choosing the letter u. But it's a pretty common letter that we choose when we're trying to make this sort of substitution. Okay. So if I replace every 3 to the x with a u, what do I get? What's my sort of new equation?
3 times u squared minus 28 times u plus 9.
Good. Okay. So all we did was move 3 to the x and change that to be a u. Okay. Now we have a quadratic equation. And we have a quadratic equation that I want us to practice factoring with. Okay. And so there's a number of ways to factor. All right, there's a number of ways to factor. And I'm going to sort of suggest that we think about factoring in terms of grouping could be one way. There's a more geometric view on factoring. So if you're a very visual learner, like I am, I'm a very visual learner. I really like the geometric one. But again, those will be things that you can explore in 15C, okay? Now, in terms of the factoring here, if I were to think about grouping, all right, that could be one technique. So we'll kind of show grouping here. Grouping basically means I keep the first term and the last term, okay? But I'm going to split up the middle term in a very clever way, right? So I'm going to leave some room for myself. So 3u squared plus 9 equals 0. And what I want to do is I want to try and split negative 28u into something that maybe has a factor of 3 in it and something that has a factor of 9 in it. Okay. Any ideas on what we could do to split our u, our negative 28u?
Negative 27 and negative 1, or negative 27.
Okay, so negative 27u, and then we would need to subtract another 1u to make negative 28, right? So in effect, we have this, oh, that's a bad color to choose. We have this negative 28u became negative 27 minus 1. So let's see what we can do from here, okay? I'm going to ask us to ignore the second part for a moment and just take a look at 3u squared minus 27u. What is the greatest common factor for that? Just this part. 3, I think that's almost true. 3u, yeah, I can take a 3u out here. So I'm going to go ahead and bring a 3u out. What are we left with? U minus 9. Okay, so this, okay, danger of too many colors here. 3u squared minus 27u became this. Okay, 3u times u minus 9. Now, if I ask us to ignore the first part and just look at the second part, and I factor out that -1, what do I have left? U minus 9. Okay. So I took my quadratic equation. I cleverly split the middle term so that I could do the greatest common factor of the first part and the greatest common factor of the second part. Now here's the beautiful part about this. If I look at everything on this side, what's the greatest common factor here? Yeah. This first term in the gray has u minus 9, but the term in the yellow also has a u minus 9. So we're going to go ahead and factor that out. What's left after I pull a u minus 9 from both terms? Exactly. We have the 3u from the gray one and a -1 from the yellow one. 3u minus 1. Okay. So this right here is factoring by grouping, right? And so I'm sure there are endless resources out there on the interweb where people will walk you through more of these questions of this type, factoring by grouping, okay? But if you sort of are like, ooh, I think I could get behind this technique, that might be something that you spend a little bit of time on. Maybe you share out in your resource share for 15C, hey, I found this great video on factoring by grouping, or hey, I found this great website that shows you every single step of how to factor by grouping. That could be an example of something you do for your resource share. Okay. All right. So all of this is in purple because it's sort of an intermediate step. Like we have not solved our initial problem yet, but rather we've set up our problem. We've been able to turn it into a quadratic. And now we're going to solve our quadratic. So we're going to continue in the purple here. Okay. So here's what I mean by that. I have u minus 9 times 3u minus 1 equals 0. How do I solve for u? Yeah, so there is something called the zero product property. And it basically states that if you have two things that are multiplied together and they equal 0, so let's say we have A times B equals 0, then A equals 0 or B equals 0. Okay. So in this case, we can say u minus 9 equals 0. And we can also say that 3u minus 1 equals 0. Okay. All right, I think this first one, I'm going to choose the slightly easier one here. I'm going to solve this u minus 9 equals 0, and I get u equals 9. Okay. But you folks help me solve the other one, 3u minus 1 equals 0. What do we get for u? Good, good. All right, so we're going to add the 1 to both sides, and then we're going to divide by 3, and we get u equals 1/3. Okay. Now, this is all fine and good, right? Everything I've done in the purple, I've solved for u. But I don't actually want u. I want x. So in order to finish the problem, we have to go back to our substitution. Okay. Now before, everywhere we saw a 3 to the x, we put a u. But now we can reverse that. We can say everywhere we see a u, we're going to put 3 to the x. Right? So if u equals 9, then 3 to the x equals 9. And over here, I can say if u equals 1/3, then 3 to the x equals 1/3. Okay. Now, these are both questions that would be fair to say, no calculator, what do you get, right? And I think on the left-hand equation, 3 to the x equals 9, we would know that x equals 2, right? What about for the right-hand equation? What do we get for x here? Good, -1, excellent, excellent. All right. All right, so here's the problem on one page. Let's kind of look at the flow of this before we move on to the next example, okay? So we started off in X land, right? We did all this work with X's to create a structure where we could say with a simple substitution, we could turn it into a quadratic equation. We did a brief review on one technique to factor, which is factoring by grouping, right? And we were able to get to U answers. Everything in the purple is in U land. But we had a question that was asked in X land. So we have to get back to like an X equals as a final answer. And so we reversed our substitution and we were able to get values for X. Okay. That's sort of the general flow of when we see these quadratic equations. And I believe that there are some like this on quiz number 3. Okay. So let's go ahead and try our hand at example number 9. All right. Now it turns out, even though example number 9 has an E in it, and maybe we think that's going to be even harder than example number 8, this one actually, I think, has far less pre-work. Okay. So here's what I mean by that. I'm going to go ahead and take this 56 and I'm going to subtract it to the right-hand side. And when I do that, I get e to the 2x minus e to the x, whoops, minus 56 equals 0. I don't see a quadratic situation yet, right? In the sense that over here, I saw like 3 to the x squared and 3 to the x. But it turns out that one of our exponential properties, okay, and again, you'll have a chance to review this in your Desmos activity for today, but one of the exponential properties says if you have e to the 2x, that's really the same thing as saying, not that, e to the x squared. Okay. Now, if I keep everything else the same, all right, just by rewriting that first term. And that's a lot of the sort of algebraic fluency that we're trying to build here. Okay, we're trying to highlight a lot of the most common situations that come up. It's okay if we don't know them right now, but when we walk out of here in December, I want us to be really comfortable with these tricks. Okay. What would be a good substitution to make in this case? Yeah, let's let u equal e to the x, all right? Now I'm going to rewrite this equation, but everywhere I see e to the x, I'm going to put a u. So what do we get? We get u squared minus u minus 56 equals 0. Let's try that factoring by grouping again. All right. U squared, I'll leave some space, negative 56. What might be a clever way of writing negative 1u?
7 minus 8 or negative 8 plus 7.
Negative 8 plus 7. I would buy that. Negative 8 plus 7 definitely gives us negative 1. So we've taken this middle term, our linear term, and we've cleverly rewritten it over here. Let's take a look at the greatest common factor for the first two terms and the greatest common factor for the last two terms. All right. What can I factor out of the one that's colored in like the blue gray, like the u squared minus 8u?
U?
Yeah, we could just take a u out, right? Because I can't take an 8 out. The first term doesn't have an 8, but I can bring out a u. So I get u times u minus 8, right? So that is the one that we colored in this lovely blue-gray situation, all right? What is my greatest common factor for the yellow part? Yeah, we could bring a 7 out to the front. What do we have left when we bring a 7 out to the front? Good. Now, a lot of times folks are like, how do I know if I'm doing things right? That's a super valid question to ask yourself. Here's a really great clue. If you find the greatest common factor of the first term and you get a u minus 8, when you find that greatest common factor of the second term, you should get the same thing, right? Because that is what allows us to say, oh, the greatest common factor of the whole thing is u minus 8. And what's left? U plus 7. Okay. So again, this is factoring by grouping, right? If you like that technique, that could be something that you practice a bit more, okay? But let's go back to that zero product property that I think Dallas was talking about, right? We have two things that multiply to make 0. That means we can say u minus 8 equals 0 or u plus 7 equals 0. And those ones, I think we can solve pretty quickly. We'll get u equals 8 and u equals negative 7. All right. Now, if you stop here when you put a box around those and you're like, great, u equals 8, u equals -7, I would be so sad for you because you just solved a different problem, right? But the question said, find x. You found u. So you're like almost there, but we got to finish off the problem. Okay. So if I want to revert to x land, what would I do with this expression u equals 8? How would I turn that back into something in x land? Yeah, we go back to our substitution. But this time, instead of u equals 8, everywhere we see a u, we're going to write e to the x equals 8. And then what would I write down here? Instead of u equals -7, I would write e to the x equals -7. All right. I want an exact answer here. Okay, I want an exact answer. How do I use algebra to get the x out of the exponent? Good, we're gonna rewrite in log form, okay? I'm gonna give an intermediate step before we get to what Dallas wrote, which is, whoops, log base e of 8 equals x. But log base e, we can just write as natural log of 8. Okay. That is my exact answer. If I apply the same thing to the other one, I would get log base e of -7 equals x, or I could say that natural log of -7 equals x. Right. These would be my exact values. I want us to go ahead and practice using a calculator. Can you give me an approximate value for x? And let's go to 3 decimal places. Okay, so Desmos or whatever calculator you happen to be using, let's find approximate solutions. All right, I agree that we should get about 2.079-ish for natural log of 8. All right, so make sure that you are getting the same value there. And I see this DNE, is that happening to other people? Like when you type in natural log of -7, what's your calculator telling you?
Error.
Yeah. Right, our calculator's telling us there's an error. Sometimes when the calculator tells us that, we panic. And we panic because we're like, I don't know, I must have done something wrong. Clearly, there's an answer and I just did something wrong. Okay. But let's unpack this a little bit. All right, we're going to go back to the idea of our graphs. In fact, if I were to sketch a quick picture of e to the x, what would that look like? If I were to just sketch a picture of e to the x, what does that look like?
Wouldn't all of the y values be positive?
Maybe, but what does e to the x look like? Yeah, it's exponential. And in fact, it would be something kind of like this, right? Like an exponential growth. All right, so let's look at let's look at this. E to the x equals 8. Can you show me on this graph where the y value of this function is 8? And I bet we would get a point somewhere maybe around here. If this is 8, then the x value is the natural log of 8. Right? Can you find a point on the graph that has a y value of -7?
Would the -7 be an extraneous solution?
It would be. It would be. Okay. So let's write out those words real quick. There are no points on the graph of e to the x that have a y value of -7. Okay, there are no points on the graph of e to the x that have a y value of -7. That's what leads us to the error. Okay, that's what leads us to the error. And so we say that this one does not provide a solution. All right. Does not provide a solution. So it's one of those moments where I'm sure we all had that math teacher at some point who was like, I need you to check your answer. I need you to plug your answers back into the equation, make sure it works. But it's also possible that as we're solving, that one of the solutions clearly doesn't work. It gives us an error, a domain error. Okay. It would be really important that we can sort of explain why there's no solution. You could certainly explain this using a picture and some words. So if you're a visual learner like me, you can do that. All right. But I think it's important to really think about like why our calculator is giving us an error. Okay. It gives us an error because we can't find a point on this exponential function that has a y value of -7, because that would be like down here somewhere. We don't even have the graph down there. So how's there going to be a point that makes that work? Okay.
Quick question on explaining it. Is it okay to say that basically the value has to be greater than or equal to 0 in order to, or I guess greater than 0?
Yes, that would be good. Yeah, you could certainly say that x has to be greater than 0, because when we think about this, we have that horizontal asymptote, so it's never actually going to get to 0. All right, so I'll put these two on a single page real quick if you want to take a screenshot of that. But being able to solve this kind of equation, thinking about when we might need to use it and why we might need to use it, and when we don't have to use it, would be all important questions to consider. Okay. All right, so there is a little summary here for us, right? And again, I know we've sort of written this out before, but if you're looking for a summary, something that you want to really say, okay, here's a process that I can use, knowing that you're going to have to make decisions along the way, but it gives you sort of a general process, all right? If you want to solve exponential equations that sort of look like this, the general idea is we're going to use logarithms, okay? And in particular, we're going to isolate the exponential. And then we're going to rewrite it in log form. And then we're going to solve for the unknown. Okay. There are some shortcuts, like sometimes if the bases are the same, we could certainly use a shortcut. But in general, this flow works for any exponential form. Okay. Now, to solve a logarithmic equation, which is really the focus of today, we're going to sort of go backwards. In fact, we are going to use exponentials to solve the log equations. In other words, it's sort of like the other side of the coin. Okay, so we're going to isolate the log. We're going to rewrite it in exponential form, and then we're going to solve for the unknown. All right. So let's take a look at a few cases. All right. My goal is to do a few examples, maybe up to 14 before we take a break. Okay, but let's see how the time is going. All right, so solving log equations. We're going to consider the same cases again. Okay, so we're going to take a look at when the bases are equal versus when they're not equal. And so in example number 10 over here, we have natural log of x squared equals natural log of 2x plus 3. What base is the log that we see in the problem here? E. Yeah. So if I were to rewrite this for myself, I might write log base e of x squared equals log base e of 2x plus 3. Okay. Now, if the bases are the same, it must be true that x squared is equivalent to 2x plus 3. Just like it was true for when we did exponentials, right? If everything else is the same, this thing that is being natural logged must be the same as the other thing that's being natural logged. So we would get x squared equals 2x plus 3. Okay. So when the bases are the same, that is very lovely for us. X squared equals 2x plus 3. All right, how do we solve for x here? All right, I buy it. We're going to have to factor. What do we have to do before we factor?
Subtract x squared from one side to the other.
You could, right? I will say this though, I don't like to factor when my x squared is negative. I think that makes it harder. So even though I have to move 2 terms, I'm going to do what Dallas suggested, which is move the other terms to the right hand or to the left hand side so that my x squared stays positive. Okay. As a general rule of thumb, I think factoring is easier when your quadratic term is positive. And so it's not mathematically wrong to move the x squared. It might just make factoring a little bit harder. Okay. Now we could certainly do factoring by grouping here. All right. But this, I think, tends to be one of the cases where folks maybe feel a little bit more comfortable eyeballing this. Does anybody happen to know what the factors of x squared minus 2x minus 3 are?
It'd be -3 and +1.
-3 is not a factor. Tell me what the factor is. In other words, what are the things in parentheses?
It'd be x plus 1, x minus 3.
Okay, thank you. I know that's nitpicky. I know what you were trying to say. All right. So when I say
Yeah.
factor, this is the factor, right? X minus 3 is a factor. All right. If for those of you who like factoring by grouping, I would encourage you to try that and see if you can match this answer, x minus 1 times x, or x plus 1 times x minus 3. But now we can apply that zero product property and we'll get x plus 1 equals 0 or x minus 3 equals 0. And we'll end up with, I did not leave myself very much space. Whoop, cheat a little bit. All right, so we get x equals -1, which looks like something in the chat, and then x equals 3. Okay. Now, to whoever said that word extraneous solutions before, I'm so glad that you brought that up. And the reason why I'm glad you brought that up is because one thing we want to be really cautious about when we are solving log equations, and let's write this in green so we don't forget, is we want to check for extraneous solutions. We want to check for extraneous solutions. All right. What that means in less fancy words, you're going to take your answer, you're going to plug it back into the very original question. And if the left side equals the right side, you are good to go. Okay. So here's our check. Let's write it out for the first one. If I were to check x equals -1, I would get natural log of -1 squared, which equals natural log of 2 times -1 plus 3. Let's just make sure that works out. -1 squared, what does that give me? Yeah, that gives us 1. All right, let's do the other side. 2 times -1 gives me -2 plus 3 gives me 1. I buy it. Natural log of 1 equals natural log of 1. That means x equals -1 is a solution. Okay. All right, let's try plugging in 3 now. Natural log of 3 squared equals natural log of 2 times 3 plus 3. Let's see, 3 squared is 9, so I get natural log of 9 equals natural log of 2 times 3 is 6. 6 plus 3 is 9. That one looks like it works out as well. Okay. So in this case, both of my answers work. So I do not have any extraneous solutions. All right. All right. Tell me what I can do for example number 11. I understand what you mean by cancel the log 13. Can you explain why? Yeah, that 1-to-1 property, right? But could I cancel them if I had log base 13 on one side and then like log base 12 on the other side? No. Okay. And so the thing I really want our eyeballs to sort of zoom in on is on the left-hand side, I have log base 13, and on the right-hand side, I also have log base 13. Since the bases are the same, I can set the two things that are being log base 13, I can set those equal to each other. And when we do that, we'll get 5x minus 2 equals 8 minus 5x. All right, what do we want to move where?
plus 5x from the right side, and then plus 2 on the left side.
Nice. All right, we get 10x equals 10. We get x equals 1. And let's plug that back in to check and make sure it works before we move on. Okay. So we get log base 13 of 5 times 1 minus 2 equals log base 13 of 8 minus 5 times 1. All right, I get log base 13 of 3. I don't know what number that is, but it's okay. Let me just see what happens on the other side. I get log base 13 of 8 minus 5 gives us 3. I don't know what the number is, but I know that they're the same number. So I can say, yes, that works out, which means x equals 1 is a solution. Okay. So in some ways, the structure of solving a log equation when the bases are the same is very similar to the exponential one. All right, so let's take a look at what happens when the bases are not equal to each other. Whoop. All right, so in looking at example 12, the bases aren't equal because I only see one log. Okay. I have my log all by itself on one side already. So if you scroll back up into the notes, right, and we look at sort of what our strategy is for log form, we already got the log all by itself. In fact, we didn't do it, it just kind of came that way. That means we can skip on over to the second step. We're going to rewrite this in exponential form. Okay. So what's my base for number 12?
Well, the base of log would be 3.
Yeah. So when I write this in exponential form, I'm going to have that base to what power?
The power of 4.
To the power of 4. Good job. That's going to equal the thing that we are logging. Okay. All right. We rewrote it in exponential form. All right. What's 3 to the 4th? Anyone happen to know? That's not necessarily a nice number, but it comes up every now and again. Yeah, we're gonna get 81. So we really have 81 equals 9x plus 2. That one I think is pretty straightforward. I'm just gonna subtract 2 from both sides. I get 79 equals 9x. Then my last step, I'm gonna divide both sides by 9. And I get 79 over 9. Okay. All right, let's check and make sure. Log base 3 of 9 times 79 over 9 plus 2. We hope that that equals 4. All right. I know there are fractions. I know there are weird numbers. But tell me what this simplifies to, just that part right there.
79.
It simplifies to 79, okay? So we have log base 3 of 79 plus 2. Switch colors. Log base 3 of 79 plus 2 equals 4. We know 79 plus 2 is 81. And we could think back to what it means to be a log. Is 3 to the 4th equal to 81? And it is yes. So that means that our answer is not extraneous, but it actually is a solution. Okay. I know a lot of us have different comfort levels with fractions and working without a calculator, but some of the worst things that you can do for yourself would be to turn 79 over 9 into a decimal, and then you round, and then you get a weird decimal, and then you get a weird decimal after you add 2, and then your answer doesn't check out. Okay, so I would encourage you to start to embrace this idea of exact solutions, because when it's exact, it's so much easier to check your answers and see if they're right or not. Okay. All right, we're going to do these last 2 examples right here, and then we'll take a break. All right, talk to me about number 13. What is the base here?
Ten.
Yeah, that base is 10, okay? And so I know for some of us, we're like, oh, how do people know this so quickly? It's okay if you're still feeling like I can't quite remember these things right now, but it's certainly something we want to start to add to our toolkit, okay? So if this were me, I would take the time to write this. It takes me less than 30 seconds to show myself what the base is. And every time I write it, it gets a little stickier that my base is 10 when I don't see it. Can I rewrite this in exponential form right now? Is there anything else I have to do before I can rewrite in exponential form? No, we've already got it isolated. So let's go ahead and rewrite. All right, I'll give you a moment to rewrite in the privacy of your own learning environment what that equation is. And I hope we end up with something like this. 10 squared equals 5x minus 11. Right? 10 squared, 10 is the base, to the power of the other side equals the thing that is being logged. All right, let's move along. 10 squared gives me 100. 100 equals 5x minus 11. I'm going to add 11 to both sides, and then I'm going to divide by 5, and I'll get 111 over 5. I will leave you to check whether this is extraneous or not in the privacy of your own learning environment. But whatever you do to check, you want to put it back into the original equation. Okay. All right, let's take a look at example number 14 and see how this is similar or different to our previous ones. All right. What are our thoughts about number 14? What should we do here?
Is the base log E?
The base, so the base we want to say is E. right? So maybe that would be helpful if we wrote 3 log base e of x minus 3 plus 4 equals 5. Now I know what my base is. Can I write this? Can I write this in exponential form right now? No. We got a lot of things we got to move first, because when I say isolate the log, I mean, I got to get this all by itself. And in order to do that, order of operations backwards says I need to do -4 and then divide by 3. So let's see what that gets us. We get 3 log base e of x minus 3 equals 5 minus 4 is 1. And then we get divide by 3, so log base e of x minus 3 is 1/3. Do not be scared of the fractions. Fractions do not mean that you are wrong, okay? And please don't turn 1/3 into 0.3, right? Again, we are looking for exact values. All right. Let's rewrite in exponential form. My base is e. I'm going to raise it to the power of 1/3. And what does that equal? X minus 3. One last step to get x by itself. I'm just going to add the 3 to the other side. Okay. All right. There's one last thing that I want to write here. And this is really because it is a structure that we will use a lot in the spring. What I just wrote down in the purple is exactly the same as what I have in the previous line. Okay. In particular, I want us to notice that e to the 1/3 is the same as saying the cube root of e. And that might be something that seems kind of familiar from quiz number 2 last week, right? I think at some point I asked you for like something to the 1/2 power. What's another way of writing something to the 1/2 power?
Square root.
Yeah, this is going to be the square root. Now, again, if you're someone who's like, I'm going to write the extra number in there, the 2 is really out here, like there's a little 2 out there. But because that's sort of our standard go-to, we don't usually write the 2 there. But if we were to write x to the 1/3, we wouldn't keep a 2 out there. We would have a little 3 out there. Okay. What would this be?
The 4th root.
Good. Good. All right. So this is something that maybe you learned at some point, but maybe no one ever told you it was actually going to be super valuable in the future, right? It's so hard when we're sort of getting all of this content to know what's going to come up again and what's not. And so that's one thing I really love about our year-long experience here is I get to tell you up front, these are going to be things we see again. Right? And I don't want to do that in an overwhelming kind of way. I just want us to know, hey, this is important, right? Because sometimes some things don't come up as much again. And then, it's not quite as relevant for us. But for those of us on that STEM path, we want to get through 150 successfully. This little algebra trick is going to be really helpful. Okay. All right. So we are going to stop the recording here.